invitation and the introduction. Thanks to Professor Kannan for this, and yeah, I'm really happy to speak in this very interesting seminar series. I saw the kind of talks and all the videos. I haven't had the chance to see many of them yet, but I'll do that soon. And it has been a very interesting collection of talks. I hope everybody is enjoying this collection. And yeah, so today we'll see certain generating functions. So the main topic of this talk are certain generating functions associated to a graph, along with some additional data that we'll call divisors, a finite collection of divisors, what we'll call divisors. So I'll introduce these in detail. And so that's the main theme of our talk. We'll study these generating functions from a very sort of classical generating functions perspective. So the kind of questions we'll ask is fairly traditional and well known. So here is an overview of what we will see. So as I said, we will define a certain generating function called Poincare series associated to a finite collection of divisors on a finite graph. And then we'll state our main result, which is a rationality result for this Poincare series. I think many of you may have seen. It's a fairly standard question that one can ask when you have a formal power series. You can ask if it is rational. And indeed, we show that in this case it is rational. And on the way to the proof, so I'll then try and sketch a proof of this result. And along the way, we look at some tools. So after stating our main result, we will look at some key tools that are used in the proof. And there are three key main tools. One is what is called as the Riemann-Roch theorem for graphs due to Baker and Noreen. This is from 2007. And a second key tool is the notion of a Jacobian of a graph. This is due to Baker, Lehart, Nagnibeda, to the best of my knowledge, from 97. Maybe there were precursors to this, it's plausible, but this is one of the early references, as far as I know, to this object, the Jacobian of a graph. At least they call it the Jacobian. And so on. And the third key tool is the theory of lattice point enumeration of polyhedra or in polyhedra. Again, this also probably has precursors, but this reference here that I have mentioned, Barbino Pommersheen 98, is a survey of this topic. So it's fairly accessible and it's something quite ready to use. So, so we look at these three key tools before looking at the sketch of the proof. So after that, we'll briefly look at the sketch of the proof of this rationality result. And then I will briefly mention some extensions to what are called metric graphs, graphs with edge lengths, real edge lengths, non-negative real edge lengths. And this is based on a preprint that I just put up on the archive very recently, just last week actually. So it's called Poincare series of divisors on graphs and chains of loops. And yeah, and for this talk, we'll focus on the graphs part. The chains of loops, which are certain types of metric graphs, I'll only mention at the end because of time constraints. Yes, yeah, and now we'll start with a general introduction to divisors and a key game, a certain game played on a graph which plays a role in the definition of the Poincare series. It's called the tip firing game. So we'll start with a brief introduction, a very gentle introduction to this. So yeah, any questions, comments before we move on to the actual heart of the matter, the body of the talk? So any questions on the overview? Okay. Yeah, the audience is there, right? Let me check. I think make sure.
Yeah, we are here.
Okay, yeah, maybe I should check periodically. Okay. Great. So let's start with this introduction to divisors and the chip firing game. So what is a divisor on a graph? So let me define what a divisor on a graph is. So throughout this talk, we'll take by a graph we mean a finite, undirected, connected multigraph. And without loops. So the graph will not contain loops, but it could contain multiple edges between pairs of vertices. So it could be, in general, a multi-graph. and connected. That's a very important hypothesis. Connected and untitled. Yeah. And finite also. All these are important hypotheses actually. Okay. Um, and now, what is a divisor on a graph? A divisor on a graph is an element in the free abelian group generated by its vertices. Okay. So what does that mean? So I associate a symbol, say bracket v, to every vertex v, and then I look at integral combinations of these symbols bracket v. And when I say free abelian group, I mean that there are no non-trivial relations between these symbols. Okay. And this is all I mean by an element in the free abelian group generated by the vertices of the graph. An intuitive way to think about this is that a divisor is simply an assignment of integers called chips to every vertex in the graph. Okay. So these integers, they can be positive, negative, or zero. We call them as chips. That's how traditionally they are called in literature. But sometimes they are also thought of as some kind of currency, some rupees or dollars. So you are assigning some currency to every vertex in the graph. It has some money. You can think of it like that. Negative money, you can think of it as the vertex being in debt, and positive money that it has some positive, it has some real actual currency there. So, uh, so this is the notion of a divisor. And how will we denote it? We'll denote it like this. So divisor D is written as sum over small v in capital V of G, where capital V of G is the set of vertices of the graph. And then you sum over AV times bracket of V. And AV will be an integer. And bracket of V is that symbol associated to that vertex V. So for instance, a couple of examples of divisors are, so if you have a graph on 4 vertices, let's say, they're labeled V1 to V4, then these are divisors, right? These two that I have given here, these two are divisors. So 2 bracket times bracket minus 1 minus 3 bracket V2, sorry, 2 times bracket V1 minus 3 bracket V2 and so on. So this is a divisor. So you're assigning chips to every vertex. So V1 gets 2 chips, V2 gets minus 3 chips, and so on. And similarly, this the second example also is a divisor that you are assigning one chip to minus 1, 0 chip to one chip to V1, minus 1 chip to V3, and 0 chips to all other vertices. So that's what we mean by this divisors, right? So some basic examples of divisors, and a basic invariant that one can associate to a divisor is what is called its degree, which is the total number of chips in the divisor. Right. So if you think of this as currency, you're measuring the total currency in your system. So and hence how is it written? It's written. So the degree of D is just the sum over all the coefficients AVs in your divisor. So you sum over all AV V in the set of vertices of G, and this is the degree of your divisor. So in our example, the first example, the degree will be minus 1. Right? If you sum over all the coefficients, you will get minus 1. And in the second example, the degree will be 0. Right? So this is a first introduction to divisors. But just having divisors like that rigidly is not very interesting. But what makes it interesting is when you can move around or transform them. You can move chips around in the graph, or transform divisors in a way that reflects the combinatorics of the graph or reflects the structure of the graph. So you like to move these chips or transform divisors in a way that reflects the combinatorial structure of the graph. And a mechanism for doing that is this chip firing game, or chip firing game. It's also called by some other names. There are closely related constructions, like there's the sand pile model and so on, that you also might have seen in literature. So all these are very closely related. So what is a chip firing game? So it's a very simple game played on a graph, one player game played on a graph. So it consists of the following. So you are given an initial configuration, which is an assignment of chips to every vertex in the graph. In other words, you are given a divisor. You are given a divisor D. And then you have a notion of a move in the graph. So this is the central notion. So you have a notion of a move in the graph where some arbitrary vertex u is allowed to fire exactly one chip along every edge that is incident on it. So the crucial thing is that this vertex should fire exactly one chip, or you can without. This is the same as saying if you do this simultaneously, it's the same as saying the vertex vertex is allowed to fire the same number of chips along every edge incident on it. So I've just considered this basic move where one chip it fires exactly one chip, but the crucial thing is exactly one chip along every edge incident on it. This is the move, notion of a move. And then what happens after that? So the game moves to a new configuration. Okay? A new configuration where the chips are updated accordingly. So this vertex U fires, right? So it loses some chips, and some other vertices that are connected to this by edges will gain some chips. So the system is updated accordingly. So what is the result of this? You get another divisor d tilde whose coefficients are say BVs. And how are the BVs related to the original coefficients AVs? So they're as follows, right? So the vertex BU, the vertex U that fired, what will be its coefficient BU? I think the audience itself can know. So the vertex fired, so it fired some chips. So what will be the new number of chips it will contain? Or it will have? Yes, the audience, just to make sure that I haven't lost you yet. Yes? Can you hear? Yes, anybody? So this vertex U, so it fired, right? So how many chips will it contain after the firing? Will it have after the firing?
It has lost some. It's a degree number of chips it has lost in the process, right?
Correct. Exactly. So it has lost exactly its valence many chips, right? So the new number of chips BU will be AU minus the valency of U. Exactly. And then so this will be the coefficient of BU. And then what about the other vertices? W, say W not equal to U. They will gain some chips, right? And how much they will gain will depend on. Remember, we are in a multi-graph, so there could be multiple edges between U and V. So it will depend on the number of. There could be multiple edges between U and W, this vertex that we are now talking about. There could be multiple edges, so the number of chips it will gain will depend on that. It's exactly that actually, the number of multi edges that are between U and V. And so we update it accordingly. So the coefficient BW will be the number of the number of edges between U and W. That's what. So the coefficient of BW will be AW plus MUW for all W not equal to U, right? And MUW is the number of edges between U and W. Okay. So this is the basic game, and then you repeat this, and you repeat this. So by repeating this, you can see that you can realize you can realize basically a vertex firing any number of chips, positive or even negative. Actually, even negative number of chips, you can realize it in terms of this basic move, because if all the vertices fire apart from U, if you get all the other vertices to fire, that is the same as getting U to fire minus one chips, if you think about it. So this is the yeah. So this way you can realize this a vertex firing any integer number of chips as long as it is the same number along every edge incident. Any questions?
Yeah, I have just one doubt.
Yes. Yes.
Yeah. So when you say that when vertex fire negative number of chips,
Yeah.
so that means is it gaining some chips
Yeah.
from?
Exactly. It's
Okay.
gaining. It will gain valency number of chips, and all the you just interchange the plus and minus here.
Okay. Okay.
And that you can realize it in terms of this move, right? If you see, it's the same as getting all the other vertices to fire one chip, and then there'll be a cancellation, and then this is exactly the same as getting this vertex to fire minus one chip. So that's why this is called the basic move, and the other moves can be realized as this move.
Okay. Thank you.
Yeah, sure. Any other questions before we move on? I think I have an example here which would make it even more clear. So here's a quick example. So yeah, we have this graph. Our graph is a kite graph. What's called a kite graph? A graph on 4 vertices. A graph on 4 vertices. So this is a graph on 4 vertices as we have shown here, and the initial configuration is this one. So V1 has -1 chips, V2 has 3 chips, V3 has 4 chips, and V4 has -2 chips. And now suppose V2 fires. So what will happen to the resulting configuration? So V2 fired. Okay, so it fired exactly 1 chip as we said, and so it will lose. How many chips will it lose? It will lose exactly 2 chips, right? Because there are its valency is 2. So the number of chips it will have will come down by 2, so it will be 1. And what about the other vertices? So V1 will gain 1 chip because there is exactly 1 edge between V2 and V3. So its new number of chips will be 0. And similarly for V3, it will again gain 1 chip, so it will go from 4 to 5. And on the other hand, V4 is not connected to V2 by any edge, so it will not gain or lose any chips. So its number of chips will remain as it is. So it's -2. So this is the final configuration, right? So this is exactly as we described in the previous slide. Okay. So any questions so far with the chip firing game? So the idea is to sort of repeat this and move from configuration to configuration. So that's the idea. So yeah. So okay. So now, if there are no questions, we can please interrupt me at any time if you have questions. Yeah. So now we just reformulate this chip firing game. This chip firing game can be nicely interpreted in terms of what is called the Laplacian matrix of the graph. So that way, I think this fits nicely into the theme of the conference. So we'll see both graphs and matrices play a key role in this talk. So the Laplacian matrix plays a key role in this, in formulating, in writing down the chip firing game in a very convenient form. So how was that? So let me explain. So let's label our vertices from V1 to Vn. Let's order them, in other words. Okay, so we label our vertices, or in other words, fix an order on the vertices. So we have our vertices as V1 to Vn. And now we can write down a matrix called the Laplacian matrix of the graph, right? I think many of you might know this. So what is the Laplacian matrix of the graph? It is not very different from the adjacency matrix of the graph, or more precisely the vertex to vertex adjacency matrix of the graph. It's essentially that, but with some redundant information. So this Laplacian matrix of the graph, which we write as Q of G, is defined as D minus A, where D is a diagonal matrix, which I'll explain what it is in a second. And A is our well-known vertex to vertex adjacency matrix of the graph. So in the ijth entry, it's an n cross n matrix, where in the ijth entry you simply have the number of edges between vertex Vi and vertex Vj. And what is this D? D is a diagonal matrix associated to the vector of valencies of the edges, of the vertices. So you consider a vector val of V1 to val of Vn, and consider the associated diagonal matrix, where val of Vi is the valence of the vertex Vi. And so this is essentially the adjacency matrix, right? Because you can recover this information, this D, from the adjacency matrix. But it's just that this has some nicer properties which makes it quite useful. So here is an example for the kite graph. For the kite graph, our adjacency matrix is the following, right? It looks like this. So the first row is 3 minus 1 minus 1 minus 1 because V1 has valency 3 and it has exactly one edge between each of the vertices V2, V3, V4. And what about the second row? The second row is minus 1, 2, minus 1, 0, right? This is the row corresponding to 2. And why is this? Because V2 has valence 2 and it has exactly one edge between V1 and V3, but it does not have any edge to V4. Right? It has one edge to V1 and V3, but no edge to V4. So hence you see this row here, and so on. So by construction, this is a symmetric matrix. Okay, and in fact, it's a positive semi-definite matrix and so on. And there's a theory. There's matrix tree theorem and so on that you may have seen. We'll encounter that in a bit soon. So this is a sort of very useful matrix to study when you're studying graphs. Okay, so now we'll reformulate the chip firing game, or we'll interpret the chip firing game in terms of the Laplacian. We'll interpret is a better word. We'll interpret the chip firing game in terms of the Laplacian. So, in order to do that, first let us realize that by identifying these vertices, so the ith vertex Vi, if we can identify it with the standard basis element Ei of Rn. Okay, so all I'm saying is, this vertex Vi, that bracket Vi, you think of it as the standard basis vector Ei, which has zeros on all entries except at the ith entry where it has 1. So what does this give us? So via this identification, you can associate vectors to divisors. So divisors are in one-to-one correspondence with the elements in Zn. Right? So giving a divisor is the same as giving a vector in Zn with this data fix. Right? So once you fix an ordering on the vertices and identify the vertices with the standard basis elements. So for instance, so all I'm saying is I'm saying something very, very simple here. Just that to make it formal, I need to sort of say all this to make it rigorous. So so here it is. So if you have this divisor V1 minus 2 V3, I'm skipping the bracket. So bracket V1 minus 2 bracket V3, then the associated divisor will be what will it be? So it will be exactly this, right? As I've claimed here. So it's 1, 0, minus 2, 0. Because the coefficient of V1 is 1, first entry is 1, and the coefficient of V3 is minus 2, so there is a minus 2 in the third entry and 0 in the other entries, because the other vertices don't appear in the divisor, so they have coefficient 0. So this is all I mean. Now, so now what do I do with this? So now with this, note that if you think of divisors as vectors, then a chip firing move can be interpreted very nicely in terms of the Laplacian. So what does it mean to fire a vertex in the language of the Laplacian? It just means the following. So suppose you have this, your initial divisor is D, it's a vector now, and your final divisor is D tilde. And now if you just look at the construction of the Laplacian and look at the chip firing game, you'll see that the initial and the final configurations are related like this. The final configuration D tilde is nothing but the initial configuration D minus the Laplacian matrix multiplied by this indicator vector. If you want the indicator vector or the standard basis element associated to this vertex U that fired. Right? If the vertex U that fired is, say, the vertex Vi, then EU will be Ei. So you simply need to multiply your Laplacian matrix with one of these standard basis vectors to realize the chip firing. So, and why is this? This is just the way the Laplacian matrix is constructed and the chip firing game is defined. You just see that, you will immediately see, right? Because this one will pick up. It will pick up It will pick up a column this will pick up a column when you multiply it by this standard basis vector EU. When you multiply the Laplacian, it will pick up a column, and if you see columns, then they exactly correspond to what we did with the chip firing game, right? So Laplace, if you see this, if you see columns of the Laplacian, exactly it has a corresponding vertex val vi, entry val, it has a corresponding entry val vi, and it has exactly these mijs that came up in the definition of the chip firing game, the number of edges between I and j. And so it's just by inspection you see that this is the case. So this is a nice way to formulate it. Now you can sort of use some linear algebra to study the chip firing game. And next step is, if you have a sequence of chip firings, so rather than one move, you have say multiple moves one after the other, a finite sequence of chip firing, then this nicely linearizes in the sense that the final configuration after you do all this, the entire sequence of chip firings is related to the initial configuration, again by multiplication of the Laplacian by a suitable vector, okay, by a suitable vector W. And what is that vector W? As you might guess, that vector W in its entries just contains the number of times the vertex Vi fired. Okay, so this is consistent with the previous the previous equation, right? So there U fired once, so there is one in that entry, in the U entry, or the entry corresponding to the vertex U, and 0 everywhere else. So this, but in general, it's the number of times that vertex Vi fired. And so here you have this basic equation that the final and the initial configurations are related by sort of multiplication of the Laplacian by a suitable vector.
So Madhu, just to clarify,
yes,
here if certain Wi is less than the degree of the ith vertex, you would still give away chips and make it negative, right?
Right, yeah. This is what is called the unconstrained chip firing game. Okay. There is a constrained version which also people study, which is what, right, where you don't allow that. You don't allow vertices which might go into debt after firing to actually perform it. So yeah, we consider this unrestricted or unconstrained chip firing game. Yes, right.
So the usual sandpile model, we would not allow that.
Yeah, exactly. Correct. Yes, thanks. Any questions? Any other questions? Is that Arvind? Arvind, it's Arvind, right?
Yeah.
Oh, okay. Hi. Yeah, any questions? All right. So now, we'll define so this chip firing game allows us to naturally define an equivalence relation among these, among the set of divisors, right? So how do we define an equivalence relation? So this naturally gives rise to an equivalence relation. So we say two divisors are linearly equivalent if they can be reached from one another via a sequence of chip firings. Okay, and you can assume that this the sequence is finite. Okay, it doesn't change anything. So two divisors are equivalent, or we'll call it linearly equivalent for some reasons. I'll come to that why we call it linearly equivalent. But we call it linearly equivalent if two divisors are linearly equivalent if one can be reached from another via a sequence of chip firings. And you can check. It's easy to check that this is actually an equivalence relation. And so this is a very basic notion of equivalence in this topic, linear equivalence. So any questions before we study linear equivalence? Actually, now we look at linear equivalence a little carefully. Okay. All right. So now let me pose some basic questions that one can ask on this chip firing game, which motivates quite a bit of the research. But before that, a first observation on this is that so you're looking at invariants of these moves of the chip firing game throughout the chip firing game, and one basic invariant is the degree of the divisor, right? So the degree of a divisor is preserved by each move in the chip firing game. So throughout this chip firing process, the degree does not change. So this is the basic observation to start off, and now you can ask a question. So before that, we identify a certain what is called a good configuration or a good divisor, a certain which is more like an ideal to have, which is what we call effective divisor. So we call a divisor effective if every vertex has a non-negative number of steps. So this is the sort of situation Arvind just asked. So a divisor is called effective if every vertex has a non-negative number of steps. So this is something you still would like to have in many situations, right? Even in sort of in a physical context, if you think of these vertices as currencies, you would like to see if you can distribute these currencies in a way that every vertex is out of debt and hence has a non-negative number of steps. So in that context, identifying this non-negative number of steps is firstly important. I mean, this collection of divisors which are called effective. So we define effective divisors like this, and then there is a basic question, okay, which is essentially what I just referred to now, which is given a divisor with possibly negative coefficients, is there a sequence of chip firing moves that transforms it into an effective divisor? Right?
Yes.
So all we are asking is, we are given a divisor which may not be ideal. There might be some vertices which are in dead, and the question is there a clever sequence of chip firings that transforms it into a divisor where this problem is solved. So every vertex is out of dead. So this is a basic question, and just by the first observation that I made, that the degree is preserved throughout the system, and the fact that these effective divisors have to have non-negative degree, right? Because every vertex has a non-negative number of steps, so it has to have non-negative degree. We see that immediately the answer is no if the degree is negative. So if your starting divisor, your initial configuration has negative degree, then there's no chance that you will transform it into an effective divisor.
Yes.
Okay. But then, on the other hand, your divisor could be positive, but then there are subtleties. So the converse is more subtle. Like it's not true in general, and so it's more subtle. And so if the divisor has non-negative degree, you can find examples where you still cannot transform it into an effective divisor via a sequence of chip firings. So just because it has positive degree or non-negative degree does not suffice. So this is the situation. So this is generally a subtle question, and this motivates quite a bit of research in this topic. And now we'll refine this. We'll quantify this a little bit. This kind of this property of being able to be transformed into an effective divisor. We'll quantify it in the next slide. So any questions? Just interrupt me whenever there is question.
Just one comment actually.
Yes, please.
So that the observation you made earlier in the earlier slide.
Yes, this one.
First yes. Observation. I think we can convert it into network flow problems also, conservation something.
Flows come up here. Exactly. I think I sort of get the flavor of what you are saying, that these network flows, there is this conservation, right? There is this sort of again a similar conservation at every vertex and so on.
Right.
But there is this something like the flows are associated to the edges, right? And then you have a sum over all the edges incident on a vertex. That is zero. That's the condition.
Right, sir. Actually, but just I want to see. Okay, sir. Please carry on.
Okay. Yeah. So as such, that exactly doesn't seem to come here. It's slightly different formulation. So at least in this literature, I haven't seen exactly what you're saying. But lattice of flows does come up in this context. So anyway, it's a topic for more discussion later. Maybe we can just move on. Thanks. So we'll quantify this now. We'll quantify this through this notion of a rank of a divisor. So we'll associate an integer to a divisor called its rank. How do we do this? So first we do the following. So given a divisor D, we associate this set bar D, which is the set of all effective divisors that are linearly equivalent to it. It's a natural thing to do, right? Given our previous question. So you would like to see, just collect all the nice divisors which are linearly equivalent to your divisor. So it's a natural thing to do. Bar D can be empty. So Okay, so this is bar D. Let's remember that bar D, and now we'll do a sort of, as I said, a quantification of this previous question, and this is due to Baker and Noreen in 2007, which is the following, which is given a divisor D, its rank Rg of D is the minimum degree of any effective divisor E, such that bar D minus E is empty, is the empty set, and then you take a minus 1 at the end. So you take the minimum degree minus 1. It's not so important, that minus 1, so we can just forget it for now. Let's focus on this. The minimum degree of any effective divisor E such that bar D minus E is empty. Okay, so what is this telling us? So remember, bar D is empty if and only if your divisor cannot be transformed into an effective divisor via sequence of step 5. So what you are asking here is, given a divisor D, how many chips do I need to remove? What is the least number of chips I need to remove from this divisor, so that after that you cannot transform it into an effective divisor via sequence of step 5. So you're sort of quantifying the question that we asked, right? So you're seeing to what extent can it be transformed into an effective divisor via sequence of step 5. So this is what it means. So it's an actual quantity, even in a physical sense. And exactly. So this is what I just said. So the minimum number of steps to be removed so that the resulting divisor is no longer linearly equivalent to an effective. Okay. And so so here there's an upper bound on the rank, a first upper bound on the rank, which is just its degree. Provided, I'll assume that the degree is sort of large enough. It's not very interesting if the degree is too small, because the rank will be minus 1 anyway. So if the degree is at least minus 1, okay, then the rank will be upper bounded by the degree. Why is this? Because if you have, if you can always take this effective divisor with degree equal to the degree of D plus 1. And then you can and so because the degree of D is greater than or equal to minus 1, there will be such an effective divisor, and then if you subtract D, if you subtract it from D, so if you look at D minus E for that, then it will have negative degree. It will have negative degree, and so it will definitely have empty linear system. This is called the linear system. It's bar, so its bar will be empty. So definitely, your rank will be smaller than or equal to that. So this is the idea. See? Smaller than or equal to the degree of D. So this is the idea. So rank is actually the first upper bound is rank is at most the degree of D, provided degree of D is greater than D. Right? Any questions on this? I hope it's clear. You just take the kind of an obvious effective divisor to sort of have an empty linear system. And and indeed the rank of a divisor of negative degree is minus 1. This is exactly the what is. Okay. And how is this related to the question that we asked? So the answer to our question is yes, if and only if the rank of D is non-negative. Right? Really by definition. Just look at it. Indeed, yes, if and only if the rank is non-negative. So so this is somehow a refinement of our question, and a basic problem here is what is called the Riemann rock problem. Again, I'll just explain the terminology in a moment where it comes from, but let's look at the problem. So the problem is to determine the rank of a divisor in terms of the underlying graph and suitable quantities. I'll just leave it vague because it indeed depends on the divisor. So you can't expect it to just depend on the graph, but it also depends on the divisor. So the question is find suitable quantities where you can actually do this and you can get a very good hold on the rank, formula for rank. So this is generally the flavor of this Riemann rock problem. Okay. Yeah. So now any questions on this so far? Rank? Okay. Yeah. On the slides we are going quite slow with this video talk. I can't see the audience, so let's see how far we can go. Okay. If there are no questions, we'll go to the main object of the talk, which is Poincare series of divisors on a finite graph. So what is this? As I said, it's a certain generating function So it's defined as follows. So you start off with a finite collection of divisors V1 to dk on G, and then you define the Poincare series PG D1 to dk of Z1 to Zk. Okay, which is for now it's a formal power series. You can think of it as a formal power series. I'll come to sort of convergence aspects in a moment, but for now it's a formal power series whose coefficients. So it's a formal power series in in k variables. K, where k is the number of divisors you chose. You chose k divisors D1 to dk. So it's a formal power series in k variables where the and you sum up over all monomials, basically all monomials. So here it is. You see, you are summing up over z1 to the n1 zk to the nk, where n1, this vector n1 to nk is in has non-negative coordinates. So it's in n to the k, where n here is the set of non-negative integers for us. Okay, the natural numbers, we take them as a set of non-negative integers for us in this talk. And so it sums up over these monomials, and the coefficient of a monomial z1 to the n1 zk to the nk is the following. So it is the rank of the corresponding integral combination of these divisors d1 to dk. So you take the integral combination n1 d1 and so on till nk dk, and you take its rank. So the rank of that integral combination of these divisors d1 to dk plus 1. So the plus 1 is not so important. So you don't need to focus too much on that. But the key is this. So you see, so the generating function basically captures the ranks of these integral combinations of these divisors d1 to dk. So that's the basic idea. Any questions on this Poincare series? Is it making sense? Okay. Yeah. So as I said here, for this talk, the n here is a set of non-negative integers. And just to clarify this construction, you can indeed take multiples of a divisor, right? If you have a divisor d, its nth multiple is basically so multiplication of every coefficient by n. So the nth multiple, n times d, where n is an integer, is simply this divisor where the coefficient of b will now be n times ab, where ab was the original coefficient. So this is this way you can take multiples, and then you can add two divisors. Indeed, they are elements of a pre-abelian group, so you can add them, and so this makes sense. So this integral combination of divisors in the Poincare series formula. So this is the construction, and yeah, and for now, just think of it as a formal power series. I'll come to convergence in okay. So now we are ready to state our main result, but any questions on the Poincare series? So we'll see a couple of examples and so on, so we'll get some feel, but before that, any questions? Okay, okay, then maybe I can move on to our main theorem, which is concerning the rationality of this Poincare series. Yeah, and let me just recall what rational is here. So we say that a power series in z1 to zk is rational if there exists a rational function f over g, f by g, where f and g are polynomials with complex coefficients, and g is not equal to 0, the denominator g is not equal to 0, such that the power series at hand agrees with this rational function f over g at every point z1 to zk in ck, where this power series is absolutely convergent. So it's a multivariable power series. You have a notion of absolute convergence, and you want this rational function to agree with this power series at every point where this power series is absolutely convergent. And yeah, and so yeah, I mean, this would vacuously hold, for instance, if your power series is nowhere convergent. But actually, in our case, it is not the case. And we this Poincare series have a non-empty open subset where they are actually absolutely convergent. And in fact, yeah, you can show with just a little bit of work that the Poincare series is absolutely convergent in the set of all z1 to zk where the absolute value of zi is strictly smaller than 1. Sorry, there is a little typo here. I think I put a smaller than or equal to 1. It's not true. You have to put a strictly smaller than 1. Okay, so sorry, correction. You have to put a strictly smaller than 1. And how do you do this? You can use this upper bound on the ranks actually. That is one method. There may be several ways actually. It's quite relatively easy. But this is one way. Just use the upper bound on the rank that I just mentioned. Upper bound by the degree, and the degree of d is at least -1, and you get that. So there is a non-empty domain of absolute convergence, and our main theorem is the rationality of this Poincare series. So we show that this Poincare series PG d1 to dk is rational, and furthermore these polynomials are actually unique. Okay, once if your series is rational, they have to be unique, and in our case we can choose them to be polynomials with integer coefficients. So it's little more than rational. Okay. So rational with the numerator and denominator having integer coefficients rather than just complex coefficients. Okay. So how much time do I have? Let us see. So this is our main theorem. So now I wanted to. Okay, we started just little. Yeah. So can I take another 15 minutes, Rajesh?
Yeah, sure, you can take. Yeah.
Oh, thank you. So I just want to sketch the tools and then just give you a flavor of the tools. So,
sure.
And then we'll wrap up. So okay. So the three key tools that I mentioned, let's just briefly look at them. Riemann rock and Jacobian and the lattice point in so one key tool for us is this theorem of Riemann rock theorem for graphs due to Baker and Rowe in 2007, which says the following. So before I state it, there is one object called the canonical divisor kg that plays an important role in this theorem. So what is this? So this is a divisor which is just defined based on the graph. So given graph G, that its canonical divisor is this divisor where the coefficient of B is simply the valence of this vertex B minus 2. -2 is not that important, but really the point is that that the coefficient is valence of B minus this constant 2. And so for instance, the Kite graph, the canonical divisor will be bracket V1 plus bracket V3, right? Because these two vertices have valence 3, the other two vertices have valence 2, so their coefficient will be 0. Okay. So this is the canonical divisor, and the theorem of Baker and Rowe gives us a formula for the rank. Okay. Let's see what it is. So it says the following. So if you have any divisor, so given any divisor, or for every divisor D, we have the following formula for rank. The formula reads like this, that the rank of D is equal to the rank of kg minus D plus the degree of D minus g minus 1, small g minus 1. That's what the formula is. So it's in some sense it's some kind of a recursive formula for rank if you want. That it's expressing rank of D in terms of the rank of another divisor, rank of kg minus C. The rank of another divisor it's kg minus C. And in the right hand side of this formula, I think we know all these terms except the small g. What is the small g? So the small g is what is called the first Betti number of the graph. So it's also called the cyclotomic number of the graph. It's the first Betti number if you think of the graph as a simplicial complex of dimension 1, and it has a simple formula. It's simply the number of edges minus the number of vertices plus 1. So it's measuring the number of cycles in the graph essentially. I mean, cycles form a vector space and it's a dimension of that vector space. So the trees will have genus 0, 1 cycles will have genus 1, and if you take 2 1 cycles and glue them along an edge, the genus will be 2 and so on. Okay, good. So this formula, as you see, can be quite useful to computing the rank. Just that the catch here is that it's recursive. So if you don't know the rank of kg minus d, then you only know the differences between the ranks of d and kg minus d. It will not help so much. But in several cases, it's actually very useful. So for instance, one immediate consequence of this is that if the rank of your divisor is strictly greater than 2g minus 2, then actually the formula simplifies very nicely. You then know that the rank of your divisor is actually its degree minus g, the genus of the graph. It's something quite nice if you see it the first time. Why is this? Because of something we have already seen, which is now what happens to kg minus d if the degree of d is greater than 2g minus 2. Okay, one thing I think I should have said before, which is what is the degree of kg, what is the degree of this canonical divisor? That can be calculated quite nicely, right? We have this handshake lemma. It's basically an application of the handshake lemma. So if you just calculate it and see, it's 2g minus 2, where g is the genus of the graph. Okay, it's an immediate consequence of this handshake lemma. And so it's 2g minus 2, and so if you consider kg minus d in this case, the degree will be negative. So the rank will be minus 1, and so you plug in minus 1 in the place of r of or rg of kg minus d, and you get this what we claim here, that the rank of d is the degree minus the genus. Okay, so this will be quite useful for us. This consequence. Okay.
Sorry,
So
one quick question.
Yes.
Is it obvious that kg has rank as non-negative rank? I mean, if you have leaves, then
Yeah.
val minus 2 will be minus 1, right? So
Correct. Yeah. So yes. So yes. No. Actually, it's not true. So so you can see that exactly as you're saying, for a tree, it will have negative rank.
yeah.
But this is the only case. Actually, the rank is actually g minus 1. It's a consequence of Riemann formula again. Its rank is g minus 1. So it will be non-negative for all the graphs of genus, non-negative genus.
So I just plug kg into the Riemann
Yeah,
law.
exactly. And then use the fact that the zero divisor has rank 0.
Okay.
And you'll get the formula for. Yeah, that's another actually nice consequence of the Riemann formula.
Okay. Thanks.
Yes, thanks. Yeah. Any questions? Yeah. Okay, let me now move on to the second tool, which is the Jacobian of the graph. So the Jacobian of a graph is a finite abelian group associated to the graph. Okay, it's called by other names sometimes, a critical group and so on, probably in sandpile literature. So what is the Jacobian of the graph? Here it is. First note that the set of divisors of G, they form a free abelian group by definition, okay? And there is a natural addition on that, and the rank of this group is the number of vertices of the graph. So let us write this, denote this group by div G. And now it has some interesting subgroups, this div G. One is, if you look at the set of all divisors that are linearly equivalent to the zero divisor. Okay, in other words, all divisors which are reachable from the zero divisor, meaning every vertex has 0 chips, via a sequence of chip firings, this will form a group. You can see this by using this, for instance, the Laplacian interpretation, or even directly, that this will form a group. If you add 2 of these, you will still be one of these. So, and one of this such a divisor, and you call such divisors the principal divisors. So these divisors that are linearly equivalent to the zero divisor are called principal divisors, and they are of this form. As vectors, they are just, you take the Laplacian matrix and multiply it by an integer vector, a vector v in Zn. So if you look at the collection of all such vectors which are of this form, they are exactly our principal divisors. And so they form a subgroup of this group div G, okay, written as prim G. And and note that because the degree is conserved by this by chip firing, the degree of every principal divisor is 0. Okay. And so this group of principal divisors are a subgroup of an even smaller group of div G, which is div 0 of G, which is the group of all divisors of degree 0. That's also a group, right? You can add up to divisors of degree 0 and so on. So this is a subgroup of div G. And so now the Jacobian of the graph is this quotient of this div 0 of G by prim G. Right? It's the construction here. So you look at the group of all divisors of degree 0 and then you quotient it by the group of all principal divisors in your graph. And this is a group. In fact, it's an abelian group, definitely. In fact, it's also a finite group, thanks to the connectivity of G. It's a finite group. And what is the order of this finite group? The order of this finite group, surprise for those who are seeing it the first time, is it's exactly the number of spanning trees of G. Isn't that really nice? It's very nice. That it's exactly the number of spanning trees of G. And this is a reformulation of the matrix tree theorem due to Kirchhoff. So it's just another way of saying this. So this is a very intricate group associated to the graph, and it's not been very well understood as far as I know. There's still a lot of work in this direction, understanding this Jacobian. And and a closely related group is obtained by taking the whole group of divisors instead of div 0 in this definition of Jacobian. So if you look at div G mod twin G rather than div 0 of G mod twin G, you get a closely related group. And just a little bit of work, you can see that this is isomorphic to the Jacobian of G plus the integers. So it just adds one rank 1 free part to the Jacobian. It's not very hard to see. It's a little exercise. Oh. And so now one last tool, and then we'll move to the proof sketch. We'll look at a special case first and then move to the sketch of proof. So one last key tool is this theory of lattice point enumeration of rational polyhedra. So polyhedron P is called rational if it can be defined by a system of linear inequalities with integer coefficients. Remember, by definition, a polyhedron is a subset of RD which is given by systems of linear inequalities with possibly real coefficients. But if you can choose these coefficients to be integer, then you call your polyhedron rational. So this is a definition of a rational polyhedron. And now, given a sublattice, or you can also just say a subgroup of ZD, okay, or Z to the D, or even a coset of that, a coset of a subgroup of Z to the D, which is called an affine sublattice. Then you can form a generating function of the set of points in the intersection of P with this affine sublattice lambda. How is that? So it's this one, right? So the point is that this is a discrete set, this affine sublattice. So you can intersect it with P and take a sum. And so here is the sum. I mean, it's a generating function. So you simply sum over all points n1 to nd in P intersect lambda of you take basically the monomial associated to n1 to the nd, which is z1 to the n1 dot z to the zd to the nd. And so this is what is called the lattice point enumerating function of say P comma lambda. And the central result in this topic is the rationality of such a lattice point enumeration function. Again, here also that these rational functions are somewhat nicer in the sense that both the numerator and the denominator can be chosen to have integral coefficients. And so there are some fine print. There's some fine print in this business which I will not get to for this talk, which is that some of these enumeration functions may not converge anywhere, and so there are things like this, but they can all be handled very neatly. And I refer to this survey by Barginock and Commercial. In fact, Barginock also has a book on this, so I'd refer you to that where all this is dealt with in detail. So it's a very beautiful topic. In the interface between combinatorics, polyhedral geometry, algebraic geometry, and so on. So this we'll use this. So this will be our tool, one of the key tool for rationality. This is how we'll get to rationality by consequence of rationality of these enumeration functions. Okay, so let me have. There's just one more slide that I have before going into the proof as such. The proof ideas, which is inspiration. So you might have seen there's a lot of weird terminology if you're seeing this the first time, and some of you who have taken some courses in say complex manifolds or algebraic geometry might have seen all these terminologies occur there also. There's a Riemann-Roch theorem for complex manifolds of dimension 1, in general complex manifolds also, and algebraic curves and so on. And so you might wonder why this is so, and in fact this line of research is actually inspired quite largely, heavily by these analogous constructions in algebraic and arithmetic geometry. In fact, this the Riemann-Roch theorem of Baker and Noreen was inspired by arithmetic geometry or algebraic geometry, and so adding to this, as I said, for a compact Riemann surface or a projective algebraic curve or an algebraically closed field, there are analogs of divisors, their rank, Riemann-Roch, and Jacobians. And so there's a close analogy between these, and they all form a part of this upcoming area called tropical algebraic geometry, which has several applications to algebraic geometry and also some applications to combinatorics. It's still to be unearthed. I think that there might be a lot more applications to combinatorics in the future. So I refer you to this book, McLagan's Strunfels, for an introduction to this topic. It's a recent book from 2015. And Poincare series for algebraic curves has been studied by Kutkowski. This is 2003, and this goes back to a work of Kutkowski and Srinivas from 93, where all this also somehow came about, at least special cases of this and so on. So this is some background from algebraic geometry to what I was saying. Okay. So now we can briefly discuss the proof ideas. Oh, okay, we have already finished some. Okay, maybe I think I'll just take 2-3 more minutes. Maybe I just wanted to give the sketch of the proof, but maybe I can just there's a special case which is already sort of illuminating. I'll just give you that, and then I'll just maybe leave the proof sketch largely. There are some key ideas which I can mention and leave it, and then we can take questions. Is that okay? Just 2-3 minutes?
Yeah, sure, you can take, yeah.
Thank you so much.
Yeah.
I think, I mean, so with the slides, I don't want to get too technical, but let me just try to give you a flavor of the proof ideas. Sorry. Oh, why did I start compiling once? Okay. Great. So before going on to the sketch of the proof, I just wanted to show you a special case which is already somehow, which sheds some light, is already somehow illuminating to the general case, which is the case k is equal to 1. So suppose you just have one divisor. Instead of these, d1 to dk for k greater than 1, you just have one divisor, d, and you consider its Poincare series. Then it reads like this, right? So you sum up over all non-negative integers of this r, the rank. Oh, sorry, here it should be rg. Sorry, I missed that rg. It should be r underscore g of n times d plus 1 times z to the n. That's what it will simplify to, the Poincare series, correct? So now, if you want to show the rationality of this series, we end up with 3 cases. Probably this is, I think it's fairly canonical. You will have to deal with these 3 cases separately, as far as I see. And the 3 cases are what if the degree of d is less than 0? It's based on the degree of your divisor. If the degree of d is less than 0, then your Poincare series has to be 0. Okay, it has to be just 0, the identical 0 series. Why? Because if you look at your divisor, it has negative degree, right? So, and you're looking at non-negative multiples of your divisor here in the formula for Poincare series, and so the rank, and so these non-negative multiples will also have negative degree, and the rank of a divisor of negative degree is -1. So the -1 will cancel with the +1 here in the Poincare series, and so you just get all coefficients 0. So this is a very easy case where the degree is negative. So that's the trivial case, so to speak. And then you have a couple of cases. So the other case is if the degree is strictly positive. If the degree is strictly positive, then you're also in a nice situation where you can apply the Riemann-Roch theorem, or the consequence of the Riemann-Roch theorem that I mentioned, to conclude that the rank of ND is actually n times the degree of d minus the genus of the graph if n is sufficiently large. Okay, how large? It suffices to take n to be such that n times the degree of d is greater than 2g minus 2. But it's based on the consequence that we derive. So you have this. And so based on this observation, you can sort of plug this in, and then if you work it out, you'll see that the Poincare series can now be written in this form. So it's then equal to a polynomial pz plus some m divided by 1 minus z squared minus the genus of the graph times z to the m divided by 1 minus z for some positive integer n. Okay. Why is this? I think just to give you a little bit of inkling as to where this is coming from, that 1 minus, that 1 over 1 minus z squared, that is coming because there is this n times degree of d here, right, in the Riemann-Roch formula. And so if you look at the series n times z to the n, you sum over all non-negative n, then how do you get the rational function? You have to sort of differentiate your power series with the sum of the z's with respect to z. So that's where it's coming from, that differentiation, and so on. And so this is the this is what it simplifies to, and this is rationality. This is the proof of rationality, basically. So this shows that this Poincare series is rational, right? You have written it as a sum of 3 rational functions. Okay. So this is the second case, and the third case is kind of, I think, the most involved somehow, which is the degree 0 case, where neither of the first two can be applied, and there we consider a homomorphism phi gd from z to jack of g, which takes where jack is the Jacobian of g, which takes n to so you take this integer n to the linear equivalence class of that multiple of d. So you take it to the linear equivalence class of n times d, and so you see that since d has degree 0, this maps into the Jacobian, right? So this is so that's why you could consider the Jacobian there, and and then you see that there are sort of two cases. The rank of n times d. There are two cases. One is it's either 0 if n belongs to the kernel of phi gd, or -1 otherwise. So why is this? This is because if you think about this, just a moment, you see for a degree 0 divisor, there are only two possibilities for rank. One is it's either a principal divisor, or in other words, linearly equivalent to the 0 divisor, and then it has rank 0. Otherwise, it has to have rank -1. And so this formula is, or this case distinction is coming based on that, because if it belongs to the kernel of jack of g, remember in the jack of g you are quotienting by the principal divisors. So that's exactly the same as saying that this divisor nd is a principal divisor. And so this is really a reformulation of that observation about ranks of divisors of degree 0. Okay, and now you are on your way, because now if you look, so so what this implies is that the Poincare series now simplifies to this. So you're summing up over all n in the kernel of phi gd intersect the non-negative integers times z to the n, because the other coefficients will sort of, that -1 will cancel with the +1 and will vanish. And now this is something nice, because what is the kernel of phi gd? It's a subgroup of z, right? It's a kernel of a homomorphism from z to something. So it's a subgroup, and subgroup of z. It's a subgroup of z, and subgroups of z are and furthermore, in this special case, it cannot be the 0 group. The kernel cannot be trivial. So the only other subgroups are of this form, m times z, where m times z, where m is a positive integer. And in this case, that m actually turns out to be the order of this element, bracket of d in the Jacobian, right? Bracket of d is an element in the Jacobian. It's a finite group. It has an order, so that is exactly that order. And the Poincare series is 1 by 1 minus z to the n. Okay, this is just after this. It's all just elementary manipulation. This is the construction. The key construction is this homomorphism. Okay. So the Poincare series is rational. So and so I just wanted to just sketch the ideas of the proof, but I think I'll not go into too much detail. It's just that the key ideas are, we just refine this PG into smaller pieces based on the degree. That's one key idea. I think I'll just mention the key ideas, and then we'll decompose the Poincare series into 3 pieces. The small, intermediate, and large, and handle each of them. I think most roughly you can compare the small piece to this degree 0 case in the special case that we considered, and the intermediate case is the case where degree of d was 0, and so the small one is degree of d less than 0, intermediate degree equal to 0, and large degree greater than 0. And the methods sort of are a bit more involved, but in spirit they are the same ideas. And the second key idea is to show that these intermediate and large pieces are both rational by interpreting them in terms of the lattice point enumerating functions of rational polyhedra. So we interpret these as in terms of these lattice point enumerating functions. So I've just sketched out some of these details, but you can just look up these. I think I hope this gives you some impression. So, but they're all, the seed is already there in this case. K is equal to 1. Yeah, and see the key idea 4 is homomorphism, which generalizes this homomorphism phi GD we just considered. So it's not all that different. Okay, so with this I think I'll conclude. So just a couple of remarks. Yeah, so this leaves a potential for a lot of work as far as I see, which is to understand this Poincare series in terms of what information it contains about the graph. So as you see, it contains information about orders of various elements in the Jacobian, things like this. So one potential direction for future work is to use Poincare series to study Jacobians. It seems like a very fascinating possible future direction. And this can be generalized to metric graphs, as I said, and in the preprint we also consider certain families of metric graphs called chains of loops and prove rationality for that. So yeah, and here are the references. So this is the Bakar Nagdipeda paper, first one, Baker and Noreen paper, and then Barbino Pomershin, and then Katkowski's paper, Katkowski Srinivas, and Stumfeld's McLagan, or maybe it should be McLagan Stumfeld. Sorry, I just interchanged the name. And then this is our preprint, the last one that we just put out in the archive. Yeah, thank you. Thank you for your attention. Oh, sorry, I think I went a bit over time. Sorry. Hold it. Yeah.
It's okay. Yeah. Thank you so much, Madhu, for your interesting talk. Yeah. So audience, if you have any question, you can ask now.
So I have a question.
Yes, sir.
About your theorem, do you have bounds on the degrees of the numerator and denominator?
No, actually, I mean, I haven't thought much about that. Yes, it seems interesting. No, I don't have very nice bounds. I mean, you could try to convert some of these, but we'll have to look carefully into this lattice point enumerating functions and the numerators that appear there, because we essentially reduce this to these lattice point enumerating functions, and so looking at that might shed some light. Yeah, it's an interesting question. No, I don't have very good answers for that. In this case,
so the lattice point enumeration part, do you have? So these polyhedra are unbounded, right? That's why you have.
Yes, you get cones. Yeah, exactly. You sum up over cones actually in this case.
Okay. So you are not using Erhard theory.
Not exactly Erhard theory. That's right. It's more this lattice point enumeration function, but it's closely related, no?
Yeah. But that would be. I mean, you would get a polynomial if it were bounded, right? But you have unbounded.
Yeah, exactly. No, but Erhard theory, isn't it sort of for this case where n is equal to 1 or k is equal to 1, so to speak, or there is this. Erhard theory is you're looking at multiples of np, right? And you're looking at the number of lattice points in a polytope. Yeah, that's right.
Yeah. So there we have polytopes which are finite. I mean, the finite number.
Right, but here also, I mean, you're sort of, you can think of this as a cone over a polytope, no? This cone, we'll get cones. We'll have to sum up over lattice points in a cone.
Okay.
And you could still think of this as a cone, but then there's the multivariate Erhard theory, which, do you know anything about that? I mean, in the sense that you sort of take a collection of polytopes, P1 to Pk, and you take sort of Minkowski sums of these polytopes. Multiples of Minkowski sums. So n1 p1 plus n2 p2 and so on, and you count the number of integer points.
This sounds familiar. This might be studied. I'll look.
That would be great if you send me some link reference if you find some, because I just briefly looked, but I could not find anything in this. Maybe I didn't look carefully. Have you seen? Okay, you've seen something like this, huh?
It sounds familiar. Let me check and I'll get back to you. Yeah, I think this is done.
Okay, that's interesting. Yeah, that will be nice to see. Yes. Thanks.
Okay. Yeah. Thanks for a nice talk. Yeah.
Oh, thank you so much.
I have to. Yeah. I have to. Yeah. Thanks.
Okay. Yeah. See you. Yeah. Thank you so much. Yeah.
See you. Yeah. Thanks.
Yes. Any other questions? Yes, the audience, I think you must have got some impressions, some questions. Please feel free to ask. So,
Actually,
yes, sir.
talk is wonderful actually, and you introduced us to many nice areas.
Thank
So
you.
one thing is that I mean, actually you are telling actually excess time. Sorry, but no need to tell. We are ready to spend another 1 hour also.
Thank you so much. Oh, thank you. That's very kind. Yeah, sorry. I think, yeah, it's hard to control the time with these slide talks anyway, and generally I find it difficult to keep on time. Yeah, thanks.
So one point, sir, actually Jacobian of G, it is equal somehow related to class number, class group, some type, some
Yeah.
sort of.
Yes, exactly. You're right. That's a very interesting point. So it's an analog of the class group of a number field, for instance. And this analogy has been quite fruitful. So for instance, there are various conjectures on class groups, right? That's also a finite group, and there are various conjectures on class groups. There is this Cohen-Lenstra heuristics.
Right, sir. Right.
And so based on that, people studied the Jacobian also using that analogy, and there have been some very nice results on this via this analogy. So studying the Jacobian of a random graph. So how does the Jacobian of a random graph look like? This is the kind of key question. Okay. And so there have been some very nice results due to Melanie Matchett Wood. I think many of you might know her. She's a student. She was a student of Manjunath in Princeton. So she wrote this very strong paper. It's it appeared in the Journal of the American Math Society JAMS. It's a very strong paper where she actually settles this question, Cohen-Lenstra heuristics for the Jacobians.
Okay, sir.
So very fascinating. Yeah, it's a very interesting direction. Yeah, very nice point. Yeah, thanks.
So one more thing, sir. Actually, now I think somehow we can connect it to Ihara zeta function also.
It's also closely related, though. I mean, we've thought a little about this. Some of us could not find very nice connections to it. There is another kind of zeta function due to Lorenzini. There is another kind of zeta function associated to a graph, a two-variable zeta function due to Lorenzini, which is really directly related to this. But this Ihara zeta function itself, it should be related, but we don't know exactly how somehow.
Right, sir. Right, sir. Okay, sir.
So it's an interesting question. If you find something along those lines, I think that will be very interesting. Yeah.
Yes, sir. When it comes, something comes, I will write to you, sir.
Sure. Yeah. You're a PhD. You're a faculty, right?
Yes, sir. I am faculty, sir, in Shivnagari University.
Okay, very nice. So in Andhra Pradesh, huh?
No, sir. It is in Delhi, New Delhi.
Oh, Shivnagari. Right. Okay. Yeah. Okay. Great. Yeah. Please. Yes.
And one more question, sir. So that you are looking free groups, right? Free abelian groups, in fact.
Yes.
So now in that free abelian groups, for example, I put some more constraints that the elements are actually vertices we are thinking as I'll take only reflexive, means like a coaxial group something.
Yeah. Yes. Reflection group. Okay.
So there also I think some sort of Poincare series is there.
That's interesting. Yeah, I'm not very familiar with that actually. So, which reference is that? Can you give me a reference?
Actually, so just now I started, sir. Actually,
okay.
Regarding the coaxial groups and all. So there I observed that. Now when I'm looking over the abelian, free abelian thing, then I just connecting these two.
It's interesting. I mean, I think one of my colleagues, Shivasubramaniam,
I know, sir.
He might be familiar with this. I think I can maybe I try to ask him, but yeah, I think he works on some similar topics as far as I know. Yeah.
Great.
Okay, thank you for the one. Yes.
Okay, sir. Thank you.
Thank you.
In this Humphreys reflection groups and coaxial groups, there they're talking about this Poincare series associated to various coaxial groups. But I think that statistic is different. There is a Poincare series associated to the length statistic.
Okay.
So I think.
Okay.
So here we are interested in rank statistic associated to Divisor.
Right. Yeah. Right. So this probably has some statistical meaning also, right? Yeah. I mean, right, okay, yeah. I usually don't think so much along those lines, so I've never thought about it. But these can be interpreted in terms of statistics. I think it has some probabilistic interpretation, right?
Yeah, I was just saying in the Coxeter group context only.
Right, there it has a statistical interpretation.
Okay, might be. Yeah, I'm not.
Oh no, you don't know. I mean, as in there is some probability distribution, and then you're actually this is some kind of expectation or something like that.
At least in the Humphreys, they just do abstract algebraic Coxeter group theory. So not much is there.
Okay. All right. Okay. Thank you.
Thank you.
Any other questions?
Okay, there is no other questions. Let us thank Professor Madhu for his interesting talk. Yeah.
Thank you so much. Thank you so much. It's a pleasure speaking. Yeah,
thank you so much. Yeah. So I have recorded the talk.
Yeah. Great.
So, yeah, I will put it in.